In this video, we're going to discuss the process of absolute dating even further and specifically focus on radioactive isotopes that have very long half-lives. To start, in this class, we're going to focus on potassium-40, uranium-238, and rubidium-87, which are three radioactive isotopes that have very long half-lives. This means they can only be used to determine the age of geologic samples or organisms that are millions or billions of years old. So if we look on the front cover of the reference table, you'll see the radioactive decay data diagram. And specifically, the bottom three radioactive isotopes all have one thing in common. They have very long half-lives that are in the billions of years. So this just shows you how they can only be used to determine the age of an organism or geologic sample that is really old, millions or billions of years old. Now, uranium-238 specifically is really important to us. This is the radioactive isotopes that scientists use to help determine the age of the Earth. So scientists find really old rock samples or even meteorite samples, and they can determine based on the uranium-238 within the sample how old the Earth is. So specifically, uranium-238 has a half-life of 4.5 billion years. That is not a coincidence because the age of the Earth is 4.6 billion years. Uranium-238 is a really abundant isotope that is found within rocks in Earth's crust. So we can use those rocks, look at the uranium-238 in those rocks, and use that half-life of 4.5 billion years to help estimate the age of the Earth. Now, before we go even further in this topic, we need to understand a little bit about the addition regarding numbers expressed within scientific notation. If you remember, all the half-life values in our reference table are expressed in scientific notation. And when we work with numbers such as the half-lives for potassium-40, uranium-238, and rubidium-87, you're not going to want to put those numbers in standard format because they're really large numbers. That's okay for carbon-14, but not so much for these. So we're going to want to keep these in scientific notation format. And with that being said, we're going to need to be comfortable adding values with scientific notation. So when you're doing this, you need to keep in mind that when you're adding values expressed in scientific notation, you only have to add the coefficients, and you're going to keep the exponent the same. Well, what do I mean by that? So let's first start with the half-life for potassium-40, 1.3 times 10 to the 9th. If we want to add another 1.3 times 10 to the 9th, we need to be comfortable with how to add this properly. So you only focus on the coefficient. You only focus on the 1.3 number. You're going to add those two together, 1.3 and 1.3, to give you 2.6. The 10 to the 9th does not get added or anything. It just gets dropped down and remains the same. So the only thing you're actually adding are the coefficients. 1.3 plus 1.3 brings you to 2.6. And again, that 10 to the 9th exponent is going to remain the same. So now we're going to look at an example question regarding potassium-40. Due to radioactive decay, an igneous rock sample now contains 25% of the amount of potassium-40 that it originally contained. And we want to know how old is this rock. So we can once again use our model of radioactive decay. In this case, we have a new isotope that we haven't worked with before. So we need to look at our reference table and find potassium-40. If we look at the disintegration column, we'll see that potassium-40 can actually decay into two other stable isotopes. One could be argon-40, the other one could be calcium-40. So we can go to either one. And the half-life for potassium-40 is 1.3 times 10 to the 9th years. So now with this information, we can start filling out our model. The radioactive isotope is potassium-40. The disintegration products, you can put both. It's either argon-40 or calcium-40. And the starting value is 100%. Remember, when you're dealing with any question regarding percentages in your model, you're always going to start with 100%. So we have 100% potassium-40. Since the half-life of potassium-40 is 1.3 times 10 to the 9th years, that's what we're going to put in this first spot here. After 1.3 times 10 to the 9th years goes by, after one half-life, 100% potassium-40 is going to be cut in half, and you're going to have 50% potassium-40, which means that other 50% is going to be the disintegration products, either argon-40 or calcium-40. Now at this point, if you see a sample with 50% potassium-40, you can determine the age of that sample, because 1.3 times 10 to the 9th years must have gone by to end up with 50% potassium-40. So that means the age of our sample at this point is 1.3 times 10 to the 9th years. As time goes on, another 1.3 times 10 to the 9th years goes by, a second half-life has passed. That 50% potassium-40 that we had is going to get cut in half again and reduced to 25% potassium-40, which means the remaining 75% is going to be argon-40 or calcium-40. To find out the age of the sample at this point, a sample that has 25% potassium-40, we have to add up all the time that's passed by. So we have 1.3 times 10 to the 9th plus 1.3 times 10 to the 9th. Remember, you're just adding those coefficients. 1.3 plus 1.3 is going to be 2.6, and then you end up with the same exponent, 2.6 times 10 to the 9th years. At this point, if we remember our question, we were looking for how old is a rock that has 25% potassium-40. Well, we did find our answer. The age of a rock with 25% potassium-40 is going to be 2.6 times 10 to the 9th years old. However, let's keep going to finish the model. After another 1.3 times 10 to the 9th years goes by, after we have 3 half-lives, that 25% potassium-40 we had prior is going to get cut in half to 12.5% potassium-40, which means the remaining 87.5% is going to be argon-40 and calcium-40. At this point, if we want to add up the age of our sample to see how much time has passed since the beginning, we have 1.3 times 10 to the 9th plus 1.3 times 10 to the 9th plus another 1.3 times 10 to the 9th. Just adding those coefficients together, we add up with 3.9 times 10 to the 9th years old. So now let's just look at one more quick example of potassium-40, but this time we're going to have a different style question. How much of a 1,000 gram sample of potassium-40 will remain after 3.9 times 10 to the 9th years of radioactive decay? So if we have our model of radioactive decay here, the radioactive isotope stays the same, potassium-40, disintegration products, either argon or calcium-40. But now our starting value, since we're not dealing with percentages here, we're dealing with a mass. We're starting with 1,000 grams of potassium-40. So now, at this point, we're going to put 1,000 grams of potassium-40 into our model. And the half-life of potassium-40 is always 1.3 times 10 to the 9th, so we're going to put that in first. After 1.3 times 10 to the 9th years, that 1,000 grams of potassium-40 is going to be reduced by half, so we end up with 50 grams potassium-40, and then 50 grams of argon and calcium-40. At this point, if you have 50 grams of potassium-40 in your sample, your sample is going to be 1.3 times 10 to the 9th years old. After another half-life passes, 1.3 times 10 to the 9th years, that 500 grams of potassium-40 is going to be cut in half again to 250 grams of potassium-40, which means you have 750 grams of the disintegration products. At this point, you add up all the time that's passed, and you have 2.6 times 10 to the 9th years old. After another half-life, another 1.3 times 10 to the 9th years, your potassium-40 gets cut in half again to 125 grams of potassium-40, and then you end up with 875 grams of the decay products. You add up all the time that's passed at this point, and you have a sample that's 3.9 times 10 to the 9th years old. At this point, we have answered our question because we want to know how much of a 1,000 gram sample will remain after 3.9 times 10 to the 9th years, And our answer to this question is going to be 125 grams of potassium 40.